Alright, here's a work solution for the reaction time problem for today's homework. Problem talks about a car and that it's under hard braking loses speed at a rate of 6 meters per second squared. The typical reaction time to engage the brakes is half a second, and it wants to know how fast should the speed limit be set to so that all cars can stop within 5 meters. Right? So we're going to start off this problem with just a simple sketch. It's kind of confusing, some of the information, and I think a lot of people are stuck before they get started because they're not sure what they should do. What's this problem really look like? So I'm going to give you a little sketch here to start with. This is how I would suggest doing it, right? This isn't just the way I would show anybody, or just doing it for instructional purposes. This is actually how I would do it here. We start off by saying, well, it's going to be moving along, and the person in the car presumably sees a child and wants to stop. And so it travels some certain distance while moving at full speed. So while it has some initial velocity, it's moving along, and then it during the time that it's reacting, it's still moving along, and then it begins to hit the brakes. And during the time it's hitting the brakes, there's also some displacement. And then it comes to rest, where the final velocity over here is 0 meters per second. Okay? And that says that the school board wants to set it so that the total displacement is equal to 5.0 meters. And notice it doesn't give us either of these bits of information. It gives us the total information. But I wanted to break this up. It seems that that's worthwhile, right? In my picture, I want to have a good idea of what's happening, and so this is information that it doesn't say specifically that this is a variable we need to consider. This is something that I think seems relevant and useful to the problem. So that's why I put it in my sketch. The other thing I want to do is to draw maybe a graph of what this looks like to kind of also help my thinking. It seems, I have the sketch here of what the displacement is doing, but it seems also worthwhile to maybe have a picture of what the velocity is doing as well. I mean, here it's kind of represented in my graphic, or my little sketch with some vectors. But if we graph the velocity versus time, what do we expect to see? Well, we know that the reaction time, delta t react, in this little window is actually a given quantity. It tells us that that's equal to 5.0 seconds. And there's also some time over here that while it's braking, and we don't have any information about that. But we do know that it starts off at some initial velocity, v initial, and it stays there. During the reaction time, the initial velocity stays the same. It doesn't change whatsoever. And then, once the brake is engaged, it begins to accelerate with a magnitude of 6 meters per second squared in the negative direction. All right? And because this is a constant acceleration, we know that the velocity will be decreasing linearly. So on our picture, we could draw that like this. Now, we don't know what this final time is here, so this isn't obviously to scale. We know, oops, actually I think I made a mistake. I kind of wrote 5.0 seconds. It's supposed to be 0.5 seconds, isn't it? Sorry about that. That looks like crud. Sorry about that. Supposed to be 0.5 seconds is the reaction time. We don't know what the brake time is, so this obviously isn't to scale. But we can relate some of the quantities that we already have on our paper that could be particularly helpful. For instance, we know we have information about the total displacement. So if we could find expressions that relate these two individual displacements, we could write a kind of a complete equation that would represent the total. So let's start with that, right? We know that the displacement during the reaction time plus the displacement during the braking time is going to be equal to the total displacement. Whoops, x total. All right? And we also know about these quantities independently. We know that the displacement during the reaction time divided by the time it takes to react is going to be equal to whatever the initial velocity is, right? That's how far the car travels. We don't know what this quantity is, and we don't know what this quantity is, but we do know what this is, so that's kind of nice. And we also need an expression about the displacement during the braking. Now we could try to use an expression like this, that the displacement while braking is equal to the initial velocity times time of the braking, or delta t if you'd like. We can put that delta back in, it's not a problem. Plus 1/2 a delta t brake, and it's just the delta t brake here squared. Now we could do that. That's a perfectly reasonable equation, but we're going to come back in the next video and talk about why we might not want to choose that in this situation.